Good afternoon, everyone. My name is Marwan Ghalib, and I'm working with the Sensor Systems and Internet of Things lab at Carleton University. And our bread and butter really is developing and testing IoT systems for a variety of domains, really. Smart grid, e-health, public safety networks, industrial IoT, and many, many different domains. And through this research, we're really looking into a lot of cool stuff like edge computing, cloud computing, big data, data analytics, visualization, AI, machine learning, and context-aware IoT, and a lot of different topics. And through the guidance of Professor Mohammed Ibn Kahla, who is a Cisco chair in Internet of Things, we're able to advance our research so much and publish a lot of conference papers, journal articles, and I'll circle back to where you can find all this and how you can reach us at the end of my presentation. So I'm a part-time student at Carleton University, and my research is IoT for the smart grid. So how IoT can enable smart grid and smart grid communications. Now, today I wanted to show you the progress of my research and talk to you about a little bit about demand-side response in energy and the state of the current energy grid and the future energy grid, which will use AI and machine learning a lot, and where the direction of research is heading in terms of the smart grid, AI, and machine learning. So today I'm talking about intelligent production and empowered consumption towards efficient and accurate AI-based energy demand-side response. So intelligent production is from the energy utility side. Empowered consumption is you and me, the consumers of energy. Efficient is really where AI ties in. We want this solution, this demand-side response solution, to be efficient in terms of resource consumption. You know, we all know IoT resources are IoT devices rather are resource constrained. So we need things to be done efficiently on the devices. We need things to be done efficiently in terms of delay in the network. And accurate AI-based solutions are really which take into account uncertainty and have accurate forecasting as much as possible. Accurate forecasting of energy usage, accurate forecasting of how different consumers like you and me will react to any demand-side response requests that come from the utilities. I'll explain all of this further throughout my presentation, but I thought I'd give you a brief description of where we're headed. So this presentation is based on a journal article, which was a survey done about artificial intelligence and machine learning approaches to energy demand-side response. I'll talk first about the current state of the electricity grid and the future state, where we're going, and where we're seeing really initial discoveries and initial applications of existing projects, and how current deployments, what they're working on for current deployments. I'll talk more about what demand response is, what the challenge is when it comes to demand response, and how AI and machine learning can help us with these challenges. After that, I'll go through the different AI machine learning approaches, and then I'll talk about the future work and where research is headed in this field. So currently, as you can see, the centralized state of the grid, where the utilities will collect information about the usage and about the state of its infrastructure. It's a unidirectional communication channel, where high voltage generators, which are centrally controlled, provide information to the utilities. On the right side, you find not just these high voltage generators like nuclear and thermal. Now you will slowly find renewable energy resources such as solar farms and wind farms at the top of the image, and distributed energy resources such as solar panels that are located on top of the roof of a house, electric vehicles as you can see in the image, also aren't just being charged by the house and by the grid or by the energy resources that the house provides, but they themselves can act as an energy source. The battery of the electric vehicle can act as an energy source, which can kick in whenever it is needed. So we need smart algorithms to process all this data that comes from the multiple sources that you see on the image on the right. So a lot of people might probably already know about the smart meters, which is a key component in this environment, as it provides granular data about the energy usage of a house. And we'll talk later about the levels of granularity in terms of the data that comes from the house. So the decentralized grid of tomorrow is bidirectional in terms of the exchange of data. So the utilities, they themselves collect information from the houses or from the infrastructure. At the same time, the utilities themselves can speak with the houses, asking them to do different actions, which I'll explain later. This is where demand response comes in. The utilities can ask the consumers to change in their consumption. This will be a signal sent by the provider or the operator, and the consumer can choose to respond to the signal. The different options that can be done by the consumer would be to temporarily switch to on-site generation if it has a solar panel on a roof or a wind turbine, or switch to on-site storage if there's a battery, or like I mentioned before, the electric vehicle battery, for example. Another option a consumer has in terms of responding to a demand response request would be to reduce or shift away the usage of energy at the house. Now, there are different types of demand response. There's price-based and incentive or contract-based. And now it requires the utilities to really take the consumer into account and incentivize them as much as possible. And the utilities themselves need to understand what the consumer behaviors are and what their preferences are. Now, the utilities don't want to send out requests and get negative responses. So if a utility asks me to switch to on-site generation or to reduce or shift my usage, like, for example, if I am asked by the utilities to not wash my clothes right now or not use the dryer right now, the utility really wants me to accept this request as much as possible and needs to kind of guarantee the response and the acceptance of this request. Demand response also applies to different areas of utilities, not just interacting with the consumer and what their preferences are. So a utility needs to control the frequency of the grid in general, and needs to control the voltage of the grid in general. Now, in terms of frequency, if the demand increase is more than the capacity, the generation capacity, the frequency decreases, and vice versa. So this issue is mainly addressed at the transmission grid level, and it's harder to control the frequency with intermittent sources like renewables, solar energy, wind energy, and so on, as well as the difficulty that comes from integrating electric vehicles in the mix and their high variability. In terms of voltage control, the distributed energy resources increase the voltage locally at a house, and they produce variable active power. Now, through the different papers we've looked into, demand response is the most cost-effective way and environment-friendly technology that can be used for frequency control and voltage control if it is well coordinated. Now, there are different generators that can kick in to help with frequency control and voltage control, but demand response and having this open channel of communication between the utilities and the consumers is what can make this more cost-effective and environment-friendly. as you can imagine, with the high influx of data that's coming in from all these different sources and the complexity of tasks that are associated with demand response, shifting energy, reducing energy, switch to on-site generation, um, so many things that can happen, and a variety of things from so many people. It's very complex, a lot of data, and there needs to be a near real-time response and decisions being made to be made, right? Now, all of this is what makes up the challenges that are associated with demand response. So AI and machine learning can help in many different ways. From these different ways, we can really highlight the top areas which AI and machine learning can help us in. So number one, it can select the optimal set of consumers that will respond to a request. It can learn the consumer's attributes and preferences. It can help with dynamic pricing of energy. It can also help with scheduling and control of different devices, provided that consent and permission is provided, and learning how to incentivize the participants in such a program. Again, the best part, and the part that maybe you and I as consumers can care about, is how are we rewarded in a fair and economic way? Fair in terms of it being worth it for me to reduce or shift my usage, and economic meaning that also the utilities need to really take their own benefits into account. And this whole process is how we can save money and save energy in our consumption, and from the utility side, how they can save money and save energy in terms of their own infrastructure and their own operation. So I came across a very interesting TED Talk provided by Sylvain Duranton. He's a management consultant leading a huge AI group. So he was talking about how AI and machine learning are coming in to take rules and procedures and use them as guides over human judgment. And there are challenges that come with that. And Sylvain talks about how we're trying to replace bureaucracy. And he talks about how AI can also do very dumb things and not be efficient if it is left alone without humans being in the loop. So I invite you to listen to this TED Talk, as it's very, very beneficial and gives you a different perspective about how AI and machine learning can be used as solutions. So this can be talked about in a whole different presentation, but I really thought this was very interesting, and I invite you all to check out this TED Talk. Now, machine learning and statistical methods that have been used with demand-side response are many. So supervised learning is one big field and one very big area that can be explored for demand-side response. Now, supervised learning in a nutshell, we're trying to learn the mapping between an input vector and outputs. So if I give you a certain input, what will the output be? And provided that there's an existing labeled set of input-output pairs. Supervised learning is used in forecasting demand and forecasting electricity prices. Artificial neural networks are used, linear regression, kernel-based, SVM, and many other methods are used to help us reach this goal of forecasting demand as accurate as possible and forecasting electricity prices as accurate as possible. Gaussian processes are used for baseline estimation. Baseline estimation is really what the consumption is before inserting demand response into the mix. So this really helps us compare between what demand response does to the energy mix and how it can help us. So we want to understand first, without demand response, what the usage is, and then we measure with demand response what the usage is, and this baseline estimation really helps us compare how effective demand response is. Gaussian processes also help us with forecasting consumption of appliances. SVR is used for short-term load forecasting as well as price forecasting. So load forecasting, and by load here we mean you and I, our consumption. Short-term load forecasting really can mean many different things, but it's a term used for intraday load forecasting. So within the day, I'm forecasting the next hour or next minute and so on. There's also long-term load forecasting, which can apply to days or weeks or months or even years ahead. Price forecasting is really if in a dynamic energy environment, we're trying to forecast what the price of energy is going to be in the short term and in the long term. Supervised learning methods are also used for forecasting flexibility of virtual power plants, and Gaussian couplet is used in load forecasting as well. Now, also EV charging demand for day-ahead demand response strategies. So taking into account when people charge their cars, their electric vehicles, and forecasting how and how much and when they will charge their electric vehicles. Photovoltaic power and short-term wind power forecasting. The solar panels on your roof, how much are they going to produce in the short term and in the long term. Supervised learning is used a lot in all of these domains, as well as forecasting inflexible loads. So loads that can't be changed easily in terms of their usage time and so on. Heating, cooling, and so on. Tree-based methods are used, like k-means clustering. Unsupervised learning, on the other hand, is when a training set is not provided. Now, this has many challenges and drawbacks and benefits, but in terms of the demand side response, we really take into account, with unsupervised learning, we take into account the complexity and the unpredictability of loads, of how people use energy, and so on. In terms of k-means clustering, research in the demand response field has really looked at the number of clusters we can use. So a lot of the research ranges these clusters between 2 and 16, and some research suggests that 14 is an optimum number of clusters to avoid overfitting. All this information can be really valuable for energy aggregators. So aggregators can be from the producer side or from the consumer side. So aggregating different generation resources and aggregating different consumer groups. So aggregators will use all this forecasting information to assess the flexibility of the assets that they aggregate, whether it's the production side or the consumer side. Reinforcement learning is used a lot in the research for demand side response. Tabular Q learning and approximation, all of these are types of methods, machine learning methods and AI methods that we can use. Now, kernel regression, temporal ensemble learning is used. Goal-oriented learning is used while interacting with an uncertain environment. Online methods such where learning happens at each time step as the data becomes available, as well as offline methods for machine learning and AI purposes. Now, There are also nature-inspired algorithmics, which were used to for demand-side response research. And again, there are different nature-based algorithms. So in terms of nature, we're really using biological process that exist all around us and trying to be inspired by them to create different algorithms. Now, for search, and they're usually used for searching and planning. And the meta heuristics approach is motivated from evolution, biological swarms, and or physical processes that exist in nature. Um, these find solutions in a reasonable time frame, and they're used for scheduling loads or appliances at the consumer level. So algorithms that are embedded in the home energy management system. And this comes back to the level of granularity of data, which I was talking about earlier. So home energy management systems, or HEMS for short, so they aggregate the different appliances that you have in your house, and they monitor the energy usage levels that come out of these different classes of appliances or different individual appliances, and they can control turning them on and off. So these home energy management system provides a high level of granularity in terms of energy usage data, well, whereas a smart meter doesn't necessarily provide this level. Um, Nature-inspired algorithmics have helped energy aggregators and energy retailers optimize the pricing of their customers who are engaged in demand response services. Scheduling loads or appliances at the consumer level, like I mentioned before, there are classes of nature-inspired algorithms. One of them is evolutionary algorithms, where no gradient information is needed, and this can help parallel implementation. Now, there are different classes, including genetic algorithms, evolutionary programming, evolutionary strategies, genetic programming, learning classifier systems, differential evolution. The list goes on and on. Now, no gradient information is needed, and they can be implemented in a parallel manner and are highly exploratory. Now, compared to traditional optimization and search approaches, this enables evolutionary computation to be used for optimization and search in problem domains where the structure cannot be well characterized in advance. Now, on the other hand, evolutionary methods have inherent drawbacks in convergence, in interpretability, and can have unpredictable results. And there's no really a guarantee of finding the optimal solution. In genetic algorithms are used in demand response for the home energy management system, optimal switching time of appliances. Retailers use them for price scheme optimization and maximizing the profit for an energy aggregator. They're also used to train neural networks and find the optimal parameter of an SVR model. NSGA2, which is short for non-dominated sorting genetic algorithm. It's used for multi-objective load scheduling. Population-based differential evolution algorithm is also used in demand response for multi-objective management of lithium-ion battery storage in a data center for demand response. And like I mentioned, it's really used for optimal power pricing in the face of the very complex and variable demand response strategies, and trying to minimize the electricity expense for the energy retailer. So again, it comes back to the overall goal of this research and of demand response in general and of smart grid research in general is to minimize the expense for the energy producers and aggregators and utilities, and minimize the expense on the user as well. So when the user is informed about the different pricing throughout the day, they can always shift their usage to a cheaper time and save energy on their bill. So it's a win-win situation for both parties. Swarm AI. A swarm in the scientific sense, is a group of is a large group of a large and dense group of insects, and they're usually flying insects. So swarm AI is also used in demand response. It does have a slow convergence speed and risk of getting stuck in local optima. And here, all the particles' histories contribute to the search, unlike in genetic algorithms where poor particles are discarded. They have less parameters requiring prior tuning and adjustment, and are usually subject to easier implementation. Their Swarm AI is used in a lot of different um, demand response areas. So optimal scheduling of appliances, aggregators using for pricing, aggregators use it for pricing scheme, and so on. Load scheduling in virtual power plants, electric vehicles, and vehicle to grid charging. So vehicle to grid charging comes back to what I mentioned earlier about the vehicle itself, how it can contribute to the energy grid. Artificial neural networks are used a lot in demand response research, where there's a single hidden layer that is what's most widely used. Feed forward artificial neural networks, deep learning, where there's not just one single hidden layer, but multiple. Um, Artificial neural networks in a nutshell, there are computational models that are inspired by the biological nervous system. They are The basic components are the nodes, and they're connected by links, and the strength of each link is determined by a numeric weight. And the nodes can be input nodes, as you can see in the image, where how data is inserted into the network. They can be output nodes, or they can be hidden layer nodes, which modify the data en route from the input to the output. Now, ANN are connectionist models where large networks of simple processing units, and they're massively interconnected and running in parallel, and they're heavily utilized in demand response for pricing, for load forecasting, for forecasting the flexibility of a load, for understanding how users are going to interact with demand response requests, and so on. Demand side response, as you can see, is really is distributed, and there are many houses spread all over the city, many neighborhoods spread all over the city as well. So demand side inherently is distributed. So, and there are multiple intelligent agents that are interacting with each other, and multi-agent systems are heavily researched in demand response as well. They are highly used, especially when there are binding agreements in place, so incentive-based demand response. They are used for the selection of the optimal set of electricity consumers that will participate in demand response schemes. And a utility wants to guarantee as much as possible that when it sends out a request to shift a load, to reduce a load, to move from the grid to other on-site generation, the utility wants to guarantee as much as possible that this request will be accepted. So really, we need to take into account the different intelligent agents and how they interact amongst each other. Future work that is being suggested in this field, and where we're really headed in AI and machine learning research for demand response, can be summarized quickly in three major areas: partial observability of DR agents. And the research so far mostly assumes that demand response agents are fully aware of the environment around it. However, in reality, it doesn't really observe the full environment. So partial observability needs to be taken into account. Um, as I recently mentioned, multi-agent systems, which consider the objectives and the actions of the different parties participating in the demand and response programs, as well as for forecasts themselves to become more accurate, to span multiple horizons in time and space, and to better quantify and take into account the inherent uncertainty of this whole process. The current trend in the industry is to take advantage of new technologies such as IoT, big data, and AI, which is the bread and butter of our research program, and automate demand response. So automating demand response is very important to highlight here, because as you understand the complexity and the complexity of the tasks and the large influx of data coming in, and all of this, dealing with this manually is definitely going to be a nightmare. So we need to really automate how the agents interact with each other, and how the utilities interact with the consumers, and how the aggregators and energy providers and utilities and distributed energy providers and sources interact with each other. And providing interoperability across all the different platforms and devices is key to advancing the research in demand response. So this concludes my presentation. And the Sensor Systems and Internet of Things Lab is constantly getting into interesting areas of research and publishing many conference papers and journal articles. And we're always looking for curious and hardworking people to join our team and help us really advance IoT in many, many domains. And you yourself can come in and join our lab and think of an even newer domain which we can integrate IoT into. So if you look at our website, it's carleton.ca/Internet of Things. You can also follow us on Facebook and YouTube, where we post a lot of our news and updates. And a lot of work that we do gets recognized by the press, by the government, by different members of the industry. And I really encourage you to stay up to date with us and get in contact with us with what you think, different videos you want to see, different topics you want us to look into and discuss and present about. So I highly encourage that you get in contact with us. And thank you so much for listening in. Have a great day.